Welcome to the 32nd International Conference on Formal Power Series in Algebraic Combinatorics, fondly known as FIPSAC. My name is Helen Jenny. Today we will have 3 speakers. Each talk is 25 minutes long with 5 minutes in between for questions and a short break. And there's going to be a coffee break at the end of the session, so I really hope you all have time to stick around. Everyone's welcome to participate. So let me introduce Angela Carnevale from the National University of Ireland, Galway, who will be speaking on generalized Igusa functions and ideal growth and nilpotent Lie rings.
Thanks, Ellen. Thanks very much. And thanks, everybody, for being virtually here. I'm going to talk about joint work with Michael Schein from Bar-Ilan and Christopher Fold from Bielefeld on our work on generalized Igusa functions and their applications to zeta functions of groups. Now, I expect some of these words to be unfamiliar for friends of FPSAC, so I will start by giving a little introduction to this area. And in fact, I find that this area is a great source of combinatorial problems and challenges. Well, oops. Okay, and this is a story that actually goes way back. For friends of permutation statistics, it might be known that combinatorial identities of zeta function were actually the place where Eulerian polynomials arose more than 200 years ago. And because of this tie between combinatorics and zeta functions, I'll give first, like I said, something is not going. Okay, I'll give a little introduction to the area and all the relevant definitions. I'll talk about the main questions and problems of interest in that area. And then I'll introduce our combinatorially defined class of rational functions, the generalized Igusa functions. And I'll talk about their applications to subgroup growth and their main combinatorial features. But first things first, let me, if it works, let me start by defining these functions. Let's consider a group G, an infinite group, and let's consider a sequence of numbers an given by the which gives the number of normal subgroups of index n of G. If you wish, you can think of the index as the smallest number of translates of your subgroup that you need to cover the whole group. This is a well-defined sequence, and the study of these sequences is the core of subject that is called subgroup growth. The main questions there are, can we compute these sequences for a given group G, and how do these sequences grow? And ultimately, what does this sequence tell us about the group? In 1988, in their seminal paper on subgroup growth, Grunewald, Segal, and Smith introduced a powerful tool to study and tackle these questions. This is known as the normal subgroup zeta function of G, and it's the Dirichlet series that encodes the sequence that I just defined in this way. So in this expression, we have a Dirichlet series that encodes our sequence an, and here S is a complex variable. Now, I won't address questions of convergence, but the philosophy here is that analytic properties of this Dirichlet series will tell us something about the growth of the sequence an, which is what we were looking for. Now, when somebody calls something a zeta function, I suspect a very famous example comes to mind. And indeed, that famous example fits in our framework. So if you consider the infinite cyclic group Z, then take a natural number n, how many subgroups, how many normal subgroups of that given index are there? Well, there's just one, the subgroups of those numbers that are divisible by n. So our sequence there is constantly 1, and therefore the subgroup zeta function, a normal subgroup zeta function of Z, is exactly the Riemann zeta function. Another example that was already in Grunewald, Segal, and Smith's paper is that of the discrete Heisenberg group. The discrete Heisenberg group is this group of upper triangular matrices where we allow these top right entries to vary among the integers. The subgroup zeta, the normal subgroup zeta function of this group is displayed here as this expression, the product of 3 translates of the Riemann zeta function. Now I should say that these 2 examples are not very representative of the complexity of the typical zeta functions of groups. But I chose to display them here because they actually are very good toy models for us to illustrate some of the key features of these functions. And also at some point, the discrete Heisenberg group will come back into my applications. Okay, but so far I've only talked about Dirichlet series, but the very name of this conference calls for a formal power series somewhere. So do we actually find a formal power series in this context? And let me try to convince you that indeed what we will be doing is computing formal power series. So if G is nice enough, so if our group satisfies some mild conditions, then our Dirichlet series, the zeta function of the group, can be rewritten as the Euler product, so a product indexed by rational primes of so-called Euler factors. So the definition is down here of an Euler factor. This is again a Dirichlet series, but instead of encoding the whole sequence, I am only choosing a subsequence indexed by primes, the powers of a fixed prime. And so now this identity is quite easy, follows quite easily from the good arithmetic properties of the sequence AN, but it's due to very deep results of Grunewald, Segal, and Smith that each of the local factors is in turn a rational generating function in p to the minus s. So in a way, we have here our formal power series to play with, and the, let me say, only 2 tasks that we're left with are to determine these Euler factors and say something about how they vary with the prime. Let me say something about what I mean with this question, or more in general, how do counts that involve a prime depend on the prime? So if we open enumerative combinatorics 1, in chapter 1, we already find one very nice example of a count depending on a prime or a prime power. Indeed, the number of k-dimensional subspaces of the n-dimensional vector space over Fq is a polynomial in Q, and not just a polynomial in Q, but a very nice one. It's a Q binomial coefficient as displayed here. If we go a little further, we change a little bit our counting problem, we find that the number of subgroups of given type and cotype of a finite abelian P group is a polynomial in P as well. This is a classical result due to Birkhoff. And again, this polynomial will be a P binomial-like polynomial. Let me say it this way. We will actually come back to this example later. And finally, so now we have seen 2 very tame objects, but things aren't always this tame. So it is a result of Dussault from 2001, exactly in the context of zeta functions of groups, that the number of FQ points on the elliptic curve that I displayed here is not a polynomial in Q. And in fact, it's not even a polynomial on residue classes. So things can be very tame, or things can get wild, so to speak. But the first 2 examples have something very strong, I'd say, in common. And the things that they have in common is a very prominent combinatorial structure that allows us to describe the count. So after I will have introduced our class of rational functions, the generalized Igusa functions, I'll try to convince you that in a way they offer some combinatorial structure that allows us to deduce in the same way some tame uniformity results for zeta functions of groups. Okay, so I think now we should be ready to actually define our gadget, our combinatorial gadget. So the main ingredient to define generalized Igusa functions is a composition of an integer. So simply a bunch of natural numbers, n1 up to nm, and a poset naturally associated with this composition. So I like to think of this poset as the poset of subwords of a word in letters a1 up to am, which is given by a1 to the n1 up to am to the nm. You can also think of this poset as the product of chains of lengths n1 up to nm. So here I displayed to the left this poset for the composition 2, 1, 1 of 4. But to actually define our function, we need to go one step further and consider the chain complex of this poset. So the poset of flags of subwords, if you like the language of poset of subwords, ordered by refinement of flags. So the object that we will actually need is the chain complex of our poset, and typical elements in there are, for example, a single word A, or a 2-chain AB, ABC, or a 3-chain like I displayed here. All of these are elements belonging to the chain complex of the poset to the left. So with the shape of this poset in mind, we can actually define our family of rational functions. So given a composition n, the generalized Igusa function associated with this composition is a rational function in two sets of variables, a set of variables y, which is indexed by the parts of the composition, and a set of variables x, which is indexed by all the subwords appearing in that poset that I showed you, and is defined as follows. For all flags or chains of subwords, we take the product over all words appearing in this chain of geometric progressions of this shape indexed with the variable indexed by the corresponding word. And for each of these, we also will need to multiply by a y multinomial coefficient, which is actually the product of multinomial coefficients, where the ith term here has is defined with, so it's an I choose, and then underneath what we find is the exponents, or better, the increments of the exponents appearing in the ith letter in each of the words of the flag. Now this is it's more complicated to say or to write than to actually compute, as we will see very soon in an example. But let me say first that this class of functions is actually a common generalization of two families of functions that were considered before, and that correspond to two extremes, if you wish, of the composition. So one extreme is that of the composition being the all-one composition, and that is has been considered previously by Michael Shine and Christopher Fall, and it's known as the weak order zeta function. And another extreme is when you have only one part compositions, and that was previously considered by Ben Klopsch and Christopher Fall, and is known as the classical Igusa function. So now we have our definition, and I told you somehow how it arose. now I have two exercises. One is for you and one is for me. The exercise for you is the following. So if you, like I just said, take the only one part composition, then the sum above here in the box actually simplifies quite a bit. And if you write it down, you can and then take common denominators, you can rewrite this whole sum in terms of a sum over the symmetric groups, and two very nice permutation statistics will pop up. So you're welcome to do this exercise while I do mine, which is to give you an example that well, doesn't fall in any of the previously known cases or considered families. So one example with a composition that is not of one part or all one composition. Well, let's take the picture from before and actually let me get rid of one part of the composition because otherwise it gets too long. And let's see, so to write down this, generalized Igusa function, what I need is to run over all chains of words, of subwords, and then for every of those, I need to write down this product of geometric progressions and the corresponding multinomial coefficient. So for instance, if we consider, say, this one here, the blue, the flag, the singleton that is highlighted in blue, then the Q multinomial part, so to speak, or Y multinomial part is trivially 1. And the reason is that, well, when the part of the composition is 1, it will always actually be 1. So be 1. So in the case of, in the second component here, we will always have 1. And for the first component, well, here the exponent appearing is only 0. So this is a trivial Y multinomial coefficient, and the geometric progression is only this one. So this will be the summand that goes into our function. In the case of this 2-element flag, again, you can easily see that both Y multinomial coefficients will be trivially 1, and this is the geometric progressions, the product of geometric progressions that we get. Instead, in this case, here, the flag that's highlighted in yellow, here we have, for the letter A, both exponent 1 and exponent 2 appear in the flag. This is the flag A square. So our multinomial coefficient here is non-trivial, is 2 choose 1, which is 1 plus y1, and both geometric progressions appear. So if you do this diligently for all flags, you get an expression of this form. Okay, so now we have seen how these functions look like, and in fact, they already look quite lengthy for a very small composition. Now we should see, or I should tell you what they can do for us. And the first main application of our family of rational functions is that we can produce explicit but elaborate expressions for all local factors of normal zeta function of the free class 2 nilpotent groups on the generators. So if you remember our example from the beginning, the discrete Heisenberg group, this is a generalization, and that is the case D equals 2 of this result. And it turns out that we can do much more. So the same conclusion, so the fact that we can write down explicit expressions for the subgroup zeta functions, the normal subgroup zeta functions, the same conclusion holds for all groups belonging to a quite large family of groups. Namely, it's a class that contains the free groups that I just mentioned, some other generalizations of the discrete Heisenberg groups, and it's closed under finite direct products. So this is already quite powerful, but one of the neat things of our class of functions is that they actually can handle base extension. So what I mean by this, well, in our toy model of the Heisenberg group, think of replacing the ring of integers with some other ring of integers of some other number field. So instead of Z, you take some other ring, and our generalized Igusa function can still handle, so to speak, counting normal subgroups. So as a corollary, we can prove the class 2 case of a conjecture due to Grunewald, Segal, and Smith. Morally, this is essentially telling us that our functions not only capture the combinatorics of the normal subgroup structure of our groups, but also capture the combinatorics of how primes decompose in number fields. So I know that I keep writing explicit, but I don't write anything explicitly because typically these expressions are very involved and involve actually several generalized Igusa functions. So it's not easy to write down an explicit example. And on top of that, to write the actual zeta function, you need a very delicate and careful work of substitution of variables. But I think I can still say something of what happens behind the scenes and how our counting problem somehow is taken care of by our generalized Igusa functions. So the good thing of the type of groups that I'm considering here is that there's a very good Lie theory that comes to the rescue and that allows us to translate the problem of counting normal subgroups into the problem of counting certain suitable lattices in a free abelian group. And this is very good news for at least two good reasons. The first reason is that I can get away with giving a talk talking about counting normal subgroups when my title said counting ideals in rings. And that's one good reason. And the other good reason is that, well, this allows for a further simplification. And let me say, so this simplification goes as follows. You can split further your count, these are infinite objects, but you can split further your count in two parts. One part is very similar to counting subspaces or subgroups in the finite world, so finite subspaces or finite subgroups, and this gives rise to counting functions such as Q multinomial coefficients. And the infinite part, which is taken care of by the geometric series. And if you remember, these were exactly the two bits that appear in the definition of our generalized Igusa functions. Here they are again. Let me finish with one very interesting combinatorial feature, one very interesting combinatorial result from our paper, which is this reciprocity theorem. So this theorem is telling us that our generalized Igusa functions satisfy sort of a functional equation in the sense that if we invert both sets of variables, all the y's and all the x's, what we get is exactly the same instance of the generalized Igusa function up to a very harmless factor, which you see here, and which only depends on the composition itself. Now, this is consistent with deep results on local functional equations of zeta functions that are due to Christopher Foyle, and that for the methods used to prove them, always exclude an elusive finite collection of prime. Our functions being combinatorial somehow allow for, so our methods allow for a generalization, for an extension of all these results to all unramified primes. So like I promised before, the combinatorics behind our generalized Igusa functions allow for all these neat uniformity results. Of course, we don't know yet. It's still open whether we can use this family of functions to extend these results beyond these classes of groups, but that's for some other time. I think I'll stop here for today. Thank you.
Thank you so much. If you'd like to stop sharing your screen and go to gallery view, maybe we can all show a reaction or clap in another way. Okay, and then I'll turn things over to our chat monitor, Olya.
So there is a question from Ben Young. So are the explicit formula that you obtained good for analytic combinatorics so that you could study the growth of subgroup indices that you gave as motivation for the zeta function?
You mean, Ben, you mean essentially if we can say something about the convergence of these guys? Yes, we can. So you know, when I talked about the fine tuning of substituting variables and so on, that way you know what the denominators will be that appear in your local factors, and those tell you what the largest poles are, which essentially is saying what the abscissa of convergence of those local factors are. And this in turn tells you what's the growth rate of the sequence. These sequences, I didn't mention it explicitly, the groups that we're talking about always have polynomial growth, so polynomial normal subgroup growth. So we know already that the sequence grows polynomially, but what we want to know is the growth rate, and the poles, the location of the largest pole tells you exactly that. I don't know if that was the question.
Thanks, Angela. So there's another question from Vic. Vic, would you like to unmute yourself and ask it?
Sure. Yeah, really nice talk, Angela. So I was just wondering, in that expression for the I of a composition, yx, can you think about those x's as being like Stanley Reasoner ring variables if you look at the order complex for that composition poset, and then the y's as like the quantum commutation of variable when you switch an xi past an xj?
Well, I mean, having a better understanding of that poset certainly would help with proving that combinatorial reciprocity result that I showed you at the end. Our proof is very much by hand instead. But yeah, certainly at the time we wrote that paper, we didn't manage to see that or to think of it in this way.
There's a question from Federico Ardila. Would you like to unmute yourself?
Sure. First of all, thank you for a great talk and for teaching us about something that's very unfamiliar to me, at least. I guess I'm used to seeing Igusa functions in the context of counting rational points and varieties. And I was wondering if it's possible to say something to help us understand the relationship between that problem and the problem of counting normal subgroups.
So you remember my slide when I convinced you that this was a talk about formal power series. The second inequality, which was telling you that each local factor is a rational generating function in p to the minus s, that's when I mentioned deep results by Grunewald, Segal, and Smith, they I think use p-adic, the formalism of p-adic integration to show that counting normal subgroups well, somehow can be traced back to some results of model theory that tell you that that those will be rational functions in p to the minus s, and that there are underlying, yes, there are underlying varieties, which in a way are telling you that counting points on those varieties are related to counting those subgroups. I am not exactly fluent in this language. Probably if Christopher or Michael want to say more about that, but as far as I know, this is model theory in a way. There's no really explicit, or at least that I know of, explicit way to connect the two.
So there are quite a few more questions in the chat. So I'll just ask one more from John Sharashian, who asked, does one encounter interesting combinatorics when trying to evaluate the zeta functions at negative integers?
Oh. So I'm not sure if that is 2 or -2. Now here somebody it would be nice if somebody would tell us something in the chat, because I don't remember, but I think, yeah, there is something. But I'm not sure if it's for subgroup, so for subgroup zeta functions, or for perhaps representation zeta functions. So some of them do have some interesting well, tell you something interesting about your counting problem when evaluated at negative integers, but I don't know at the moment.
Great. Well, let's all thank Angela again for getting us off to such an excellent start this morning.
Thank you.